We've been thinking about average velocity over a period of time. We know that if we want the average velocity between 8 o'clock and some other time b, then that's given by this formula. We have the change in position divided by the change in time. But if we want the instantaneous velocity at 8 o'clock exactly, then this formula is a little bit problematic. If we try plugging in b is 8:01, then that's giving us an average velocity over a period of 1 minute. And that's not the same thing as the instantaneous velocity at 8 o'clock. We could try b is 8 o'clock and 1 second, but that's still an average velocity. Now, it's an okay approximation if we're talking about the velocity of a car. So the car's velocity is not going to change very much over that 1 second. But if we're talking about a dragonfly, then its velocity fluctuates all over the place. The issue is this other variable b. If we want an instantaneous velocity at 8 o'clock, there's no good way to choose one specific value for b in this formula that's going to work in every situation and that everyone can just agree on. We know that the closer b is to 8, the better, but we can't plug in b equals 8 because we'd get 0 over 0, and that's just ridiculous. So our solution is to take a limit as b approaches 8 o'clock. So our formula for the instantaneous velocity at 8 o'clock is a limit as b approaches 8 of f of b minus f of 8, that's the change in f, divided by b minus 8, the change in time. In other words, we're taking a limit of average velocities as b approaches 8, or as the time interval gets shorter and shorter. This is a massive concept. The idea that you can take the limit of a bunch of average velocities and get an instantaneous velocity. And we want to apply this not just to instantaneous velocity, but we want to talk about instantaneous rates of change of any function. So let me erase this. If we want the instantaneous rate of change of a function f of x at some point x equals a, we're going to give this a special name. So we're going to call this the derivative of f of x at the point x equals a. So this is our big idea. The derivative at a point is measuring the instantaneous rate of change of the function at that point. And the formula for it is exactly the same as what we had below. We've got f of b minus f of a divided by b minus a. So that's an average rate of change. And then we take the limit as b approaches a. And that's the derivative. So we give this a special notation. We're going to say that the derivative of f at a will be denoted by this f prime of a. So all of these things, this notation, this formula, this idea of an instantaneous rate of change, all of these are wrapped up in this word derivative. And that's what we're going to be learning about for the next several weeks. So let's start getting used to it.